Hey everybody. So we have been talking about finding the area under curves, under graphs of functions, let's be more precise, right? The area between a function and its between the x-axis and the function over some kind of interval, right? And so we've discussed approximating these areas with rectangles. We take limits as the rectangles get more numerous. There's more and more of them, which means at the same time they're getting smaller and smaller, or at least their widths are, and their approximations get better and better. And so in the limit, we say that that gives us the area of these regions we're talking about. We haven't really talked about why we might care about this area, other than it being maybe some geometrical interest. Let's try to put a little meaning to this. Okay, so let's talk for a minute about distance, and we'll talk about distance and velocity and some related ideas. Okay, so let's start with something very simple. Let's say I have a particle that travels with a constant velocity. It's traveling, let's say, at 2 meters per second for 5 seconds. Okay, so we might ask, how far did it go? And this should be a pretty standard thing to do. The distance it traveled should be its, let's say, its velocity times time. How long did it travel for? So in this case, it's 2 meters per second times 5 seconds gives us 10 meters, right? Simple enough. No big revelation here. However, what if I tell you that a particle, let's say starts at rest and increases to, I don't know, let's just say 6 meters per second from the time it starts until 10 seconds later. Okay, so it's sitting there at rest. We start the clock, it starts moving and increasing its speed from 0 to 6 meters per second. How far did it go? This is a much more difficult question to answer. We would need to know, right, this idea of velocity times time hinges on the fact that it's going the same velocity that entire time, right? I can't multiply it 6 meters per second times 10 seconds because I know in the beginning of the trip it was going slower, and then at the end it was going much faster. But one thing I might do is make some approximations, right? So let's say here's a little timeline. Here's t equals 0. Here's, let me give myself a little more space. Let's say t equals 0 is right here. And let's just put t equals 6 right there. Okay, so there's my t values. So maybe I could say something like, oh, I don't know, by 5 seconds, oh, sorry, this is not 6, this should be 10. I confused my time and my speed. So this is 10 seconds. Okay, so we start at 0, we go through 10 seconds. Let's suppose at t equals 5, so 0 seconds, 5 seconds, 10 seconds. We know its speed at 10 seconds was 6 meters per second. Maybe we can estimate that at 5 seconds, its speed was 3 meters per second, right? We're just making a little estimate here. And further, what I can do is say, well, why don't I just suppose it was going 3 meters per second for this whole interval, right? And it was going 6 meters per second for this whole interval, right? This is not perfect. We're making an estimate, right? So then during this interval, the distance covered would be, let's call this d1. We would have 3 meters per second times 5 seconds. Oops, that's not a denominator. Times 5 seconds. The d2 is going to be 6 meters per second times 5 seconds, right? 5 second interval. And so this approximation would give me 15 meters in the first 5 seconds and 30 meters in the second 5 seconds. And so the total distance would be the sum of these two, which is going to be 45 meters. Okay. Now, you might be wondering, you know, this could be a very bad estimate. Maybe my speed stayed almost zero. Maybe this thing was barely moving in the beginning and suddenly sped up to 3 seconds. And then it stayed fairly close to 3 meters per second and then suddenly sped up to 6 meters per second. This would be a big overestimation. So what I could do is I could say, well, why don't I check its speed at smaller intervals, like at every 2.5 seconds, right? And I would have a better estimate of its actual speed. And if I went even further, I would get a better estimate of its actual speed. So if I had more information about its speed at each moment, I could have a better and better estimate. For instance, maybe I had a speedometer on this thing, I had some kind of recording device that measured its exact speed at every 1/10 of a second. That would be a lot of little moments, each of these little moments of a 1/10 of a second to add up, but we could do it. Okay, so let's leave this idea for a moment and now come back to what we've been doing. So let's say, so now let's go back to functions. Let's say I have a function, v of t, equal to 1 over t plus 1, that gives the velocity of a particle in meters per second. Okay, so that also implies that t is in seconds. I'll just write that, make it explicit, for t in seconds. So t is our time, right? We start the clock at some arbitrary 0 point, and our particle moves with velocity given by this formula. Okay. What if we wanted to estimate its velocity, or sorry, estimate the distance traveled from t equals 1 to t equals 4? Well, I could do exactly what we did over here, right? So I'm going to start, right, because this is a velocity that's changing at each value of t. At t equals 1, it's traveling at 1/2 meters per second. At t equals 1.1, it's 1 divided by 2.1 meters per second, right? At each little moment of time, the velocity is changing. So we run into the same problem we ran into in that example. But let's suppose we try the same thing. So I'm just going to draw myself a little number line. Oops, let's look at t equals 1, t equals 3. Let's divide this up into intervals, subintervals. So I'm going to divide it into 4 subintervals, right? So that would make this 2. This is going to be 1.5. This is going to be 2.5. Right? So what I'm going to do, remember what we did over here. I'm going to pretend at each interval it's traveling the speed during that whole interval that it was traveling at the end of the interval. In other words, for this interval here, I'm going to pretend its speed was v of 1.5. For this interval here, I'm going to pretend its speed was v of 2, v of 2.5, and v of 3. And notice the time, the amount of time it travels, right, is the same for each of these intervals. We'll use some familiar notation here. Delta t is equal to 0.5, right? That's just, this whole thing was 2 units long divided by 4 intervals, gives us 1/2 a second for each interval. Okay, so I could add up, I could multiply this velocity times delta t. That would give me the distance, the approximate distance during this interval. Remember, I'm making a big assumption here that its velocity was traveling, was constant during the interval. We know it's not, but that's fine. We're making an estimate. I can multiply or add to that the approximate distance during the next interval. I can add to that the approximating distance, it should be a 5, the approximating distance over the next interval, and add to that the final interval. Okay. And this is what I would say is my approximate distance. Let's just use D for that. The distance traveled during those 2 seconds. Again, it's an approximation. Okay. Now, let's do something else here. Let's add a little bit to this picture. Okay. Geometrically, V of 1.5, well, let's do it this way. We know the function V of t equals 1 over t plus 1. Its value at 1 is 1/2. I'm just going to put that right here. Its value at 2 is 1/3. Its value at 3 is 1/4. So it's a decreasing function. It has a familiar curve. Not a perfect drawing, but you get the idea. We've generally got a decreasing function. I made it worse. Let's try this again. Someday I'll be good at this thing. Okay. So that's representing this little interval of a function, right? This function goes on and on. It's approaching 0 here. It's got an asymptote way over at -1. We're just looking at a little piece of it. Let's look at this first approximate distance. We took delta t times v of 1.5. V of 1.5 would be this point on the graph. When we multiplied the width of this interval times the height of the function here, this approximating distance is exactly the same as the approximating rectangle in this graph. The next approximating distance, or approximate distance, either one works depending on how I want to say it, would be this rectangle. Right, each of these points, for instance, I'll do this one's an easier one to write, 2 v of 2. That's the height. Width is delta t, which happens to be 0.5 in this case. And then there's our last approximating rectangles. Again, we're all going to squint and pretend that I drew these nicely, and those intervals are all the same distance. Okay, so what are we showing here? Well, this idea of area in this particular case is for a velocity function whose input is time. When we integrate over this time interval from t equals 1 second to 3 seconds, we get the distance traveled during that time. Okay, right? And you can just see in the process here that it's exactly the same thing we would do when we forget all this calculus stuff and just think about something moving and how we figure out distance and time. Distance given a velocity and the time, right? So these approximating rectangles give us an approximate distance. And if we chopped it up into more intervals, we would get a better approximation, right? I would fill this rectangle up to here. This one would now go up to here. This one would now go up to here, so on and so on. And then we could do more and more rectangles, and we're getting better and better distances, approximations. And so in the limit, the true distance is going to be what we've been coming up with for area. We can also talk about it in terms of units. What is the units of velocity, v of 1.5? That's meters per second, times delta t. T is in seconds. So if you multiply meters per second times seconds, you get meters, right? You kind of work with units that way. That another way to tell that what we're dealing with is a distance. And whenever we do this process with our functions, right? If we had something like, if I had a function, let's say I had a function that was pressure per depth maybe in meters, meaning as you go down in some liquid, what's the pressure look like as you go down deeper. So maybe this axis, the d-axis, as I increase is greater depth. Then you could think about what this area under the curve means. If this was something like, maybe this is pressure gained per meter. That would be a better way to do this. So it's maybe pascals is the unit. So this would be pascals per meter. Distance is in meters. If we took these little areas approximating rectangles, would be pascals per meter times meters equals pascals, right? That's a unit of pressure. And so that's right. We can always take, if we're taking these areas, if you want a clue as to what it represents, looking at the product of the units of the function times the units of the input will give you at least the kind of thing you're getting. And you can think about what it means at the end. If I have a profit per item function, whose input is the number of items, then when we multiply those two things together, we get total profit, right? And so this can give us a clue or give us an intuition about what these areas are telling us. Okay, so let's finish this up a little bit. Let's do a little bit more work on this problem, so we can do one more technical thing when we're done here. So first of all, this is easy enough to compute, right? I just evaluated v of 1.5, v of 2, just plugging it into the original function. The approximation I got here was 0.6345. And using some of the calculus you'll learn later, the exact value of this area is going to be the natural log of 4 minus the natural log of 2, which to 4 decimal places is 0.6931. So not a terrible approximation, not terribly great either, but for only 4 intervals, that's not too bad. Okay. So let's write this, instead of doing it for 4 intervals, let's write this distance approximation for n intervals. Let's generalize this. And then I want to show you a nice program that's available online, Desmos, that will, there's many that will do it. This is one that I use a lot because it has graphing, even though we're not going to use graphing for this particular exercise. It's just where I go a lot because of the graphing functions. So let's remember how to generalize this. If I were to find the area from, so the area under v of t equals 1 over 1 plus t plus 1, from t equals 1. Oh, I wrote 4 up here, but I meant 3. Sorry about that. I did what I wanted to do down here, but I said something different up there. From t equals 1 to t equals 3, right? So our formula for this area, remember, is the limit as n goes to infinity of the sum of I equals 1 to n of v of t sub I delta t, where n is equal to the number of intervals, and delta t is going to be the difference in the endpoints, 3 minus 1 divided by n, equals 2 over n. And t sub I, I'm going to use right endpoints again. We just say we start at the first endpoint and we add I delta t. In this case, that means t sub I is equal to 1 plus I times 2 over n. Or more compactly, we could write this as, I'm trying to decide what's nicer. I'm going to just leave it as 1 plus 2i over n, okay? So there are our pieces. So our area would look like the limit as n goes to infinity, I equals 1 to n of 1 over, so I'm doing v of t sub I, so I'm putting t sub I into the function 1 over 1 plus t. So I'll get 1 plus 1 plus 2I over n times delta t, which is 2 over n. Okay, we can probably we can obviously simplify some of this, but what I really want to show is a couple things. First of all, this is just a nice compact formula for the actual area, which in this case represents distance, right? So area is like the geometric presentation, but it can represent many different things. And in this case, that area is representing a distance traveled because it's a velocity function. So let's hold on to this thing and jump over to a different program for a second. Let me jot that down. We've got sum of I equals 1 to n, 1 over 2 plus 2I over n times 2 over n. Okay. So we're going to jump out of this for a second and jump into Desmos. Okay, so this is a nice graphing function. Let's do a few things with it while we are here. First of all, it can recognize function notation. So if I write, it needs x as an input. We were using t, but it wants x as an input. It can use t, but it interprets it a little bit differently as far as I know. So all I need is x plus 1. Okay, so there's a picture of our function. I can restrict it to just the values I wanted. Remember, we were looking at I want x between 1 and 3. So I'm just typing in that less than sign and typing equal after gives me the less than or equal to. So notice now that graph, right? First it showed everything, but when I put in this little restriction, we get that. So I'm going to zoom in on that area. This was the area. I'll show you a few tricks with this while we're looking at this. I'm going to pretty this up a little bit. Let's make it a little bit bigger to look at. Let's also get rid of all these grid lines. I don't need all those right now. So that's the area, or that's the piece of the curve we were looking at. I can shade the area if I want. I want to shade everything. I want y to be shaded for 0 is less than f. Oops, no, I want y is less than f of x. So now it's shading below that graph if you want that picture. But what I really want to show you is how we can do the summation notation. So if I type sum, oh, and let me write down our formula. We had come up with the area to be the limit as n goes to infinity of the sum of I equals 1 to n of 1 over 2 plus 2I over n times 2 over n. And one thing that we can do with this, I can program this in, not the limit, but I can put in the sum. I'm just typing sum, it gives me that symbol. I want to change my index to I so I can match what I have over there. I equals 1. I'm just manipulating by pressing the arrows. I'm going to go up to n. And then I'm going to have 1 divided by, just using the slash, 2 plus 2I divided by n times 2 divided by n. Okay. Now, notice it doesn't know what n is, so I'm going to use its suggestion to add a slider. It gives me, I can change the values of n, and it spits out the values of that summation for different values of n. It doesn't know what to do with a negative n, because then we're going from I equals 1 to a negative number. But I can fix this. I can just put 0 as the lowest, or let's put 1 as the lowest value of n. Let's go up to 50,000. And decimal numbers don't really make sense here. So I'm going to, when it says step, it's how big do we, every time we move the slider, it has to move at least by 1. It's the smallest increment you can change by. Okay. So right now, up in this 0.5 is telling us the sum if n only equals 1. So it's only going up to 1 up here. But this 0.5 is going to change as I increase n. In other words, what I'm doing here is having the computer compute for me what the approximate area is for more and more rectangles. So as I go, right, here's up to 300 already, so I'm going up to 50,000, so it slides pretty fast. So I slide up to 50,000, it's making more and more and more changes, and we see this 0.693142, right? We had done an approximation up to 4 rectangles. So if I did n equals, oops, I didn't change that, I thought I did. Let's go up to 50. We can go down here to 4 rectangles, and there was that 0.6345. They give us a few more decimal places. And as our number of rectangles increases, we get a better and better approximation, okay? So this is a nice little program for helping you compute stuff, and it might help you get used to this function, the summation notation, things like that. I really like Desmos. I use it a ton for graphing. There's tons of options in here for the kinds of things you can do with it. I definitely encourage you to play around with it. You'll see it in more of these videos as we go forward. Okay, that is it for this one. Thanks, everybody. I will see you next time.